Hello everyone, I'm Meghna Kiran and I'm super excited to walk you through one of my recent projects where I explored sequential pattern mining using a hand-made toy dataset on urban mobility. If this is based on my Medium blog that's now live, and I'll be explaining every single section here. So let's start with the basics. Sequential pattern mining is all about finding patterns uh, and how events occur over time. Unlike just the frequent item sets which we use in a priority or FP growth, the order of the events matter in sequential pattern mining, and that's the key. So, for instance, taking my data set into consideration, if a person goes from grocery store to restaurant, it is not the same as going from restaurant to grocery store. So, the sequence actually gives meaning, and the context completely changes. So, unlike some traditional association rule mining, these sequential pattern mining preserves the temporal dimension. Uh, they not only tell what events occur together, but also in which order they actually unfold. And this is especially vital in domains such as human mobility analysis, where sequence of locations visited reveals underlying behavioral routines, intentions, and constraints. So here I have used mainly three algorithms, which is prefix span, GSP, and SPADE on a handcrafted mobility data set. So why do we need sequential pattern mining? As discussed already, the order matters. For example, if we consider the field of retail analytics, while frequent item set mining might reveal that customers often purchase bread and butter together, sequential pattern mining says that whether bread is purchased before the butter or butter is purchased before the bread. Though this might not be a example to make you understand what sequential pattern mining is, the data set that I've taken below would definitely make you understand. So here, the real world applications of sequential pattern mining are healthcare monitoring, cybersecurity and recommendation systems, and many more. As it captures the order of the events, it stands apart from the association rule mining or FP growth or a priori algorithms, which disregards temporal constraints. Um, so we have types of sequential patterns. First one comes the frequent sequences. This is the most fundamental level where we just find out the frequent sequences without any closed or maximal sequences, just based upon a minimum support threshold, which is user defined. It can be 20% or 30%. And these sequences capture what happens and mainly in what order. And we have closed sequential patterns and maximal sequential patterns as well. A sequence is closed if there exists no superset with the same support, and maximal sequential patterns means that if there exists no super sequence that is also frequent. Then this is the sequential rules. Though this is not the central focus of the work in the blog, the sequential rule mining bridges the gap between the pattern discovery and the decision making. It goes a step further assigning the probabilities or confidence, such as 78% here, to transitions. So here there are some evaluation metrics and mathematical formulae that we have used here. First thing is the support. It refers to the proportion of the data sequences in which a particular sequential pattern appears. So support of P is equal to the number of sequences containing that particular candidate sequence by the total number of sequences that gives the support. And then we have the confidence, the support of A given B, the support of the sequence by the support of A is confidence. And lift here we have is the confidence by the support of B. So if lift is greater than 1, then it is positive, positively correlated. Lift is equal to 1, then it is neutral. And if lift is less than 1, it is negative association. For example, if from school to cafe has a higher lift, then that means that there is a strong behavioral linkage post academic activity in the cafe. And these are some constraints which I've already discussed: support, confidence, the maximum length, uh, and the gap constraints, minimum gap and maximum gap, which specify some allowable time or event gaps between elements in a particular sequence. And then we have the dataset design and the collection strategy. Most of the academic papers or blogs, which include sequential pattern mining, only use recommendation systems or retail marketing or some web click streams. However, these datasets often lack some spatial temporal context, which is precisely what makes mobility data interesting. So for that, I took the inspiration from the geolife trajectories dataset, which contains latitudes, longitudes, the timings of the user, where he has moved from where to where. It contains all of that. It contains around 17,600 files. So I've taken inspiration from that dataset and I created a synthetic toy dataset, which contains the modal transportation, the latitudes and longitudes, the time, the user ID, which is the user here, and the temporal variance and the location labeling, again school, bus stop, library, restaurant, etc. And so this is how the data set structure is: user ID, date, time, location, latitude, longitude, and the transportation mode. This is how the CSV file is. We have taken this here and converted it like this to understand the data set more better. So user one, based upon the CSV file, from library is going to grocery store, from grocery to restaurant, restaurant to school, and school to bus stop at different points of the time in different days. So this one mobility belongs to one day. This belongs to another one. So as for all the users here, I've taken 10 users and then I've made it into a list because we will be feeding this list to algorithms. So this part was mainly about cleaning up the data. I dropped the unnecessary columns like latitude and longitude and sorted the sequences by time and converted them into sessions and stored them in a sequential format. So this is how previously it was, and it was converted into a list now, as we have seen in the notebook. And then coming to the algorithms, first one was prefix span, which is prefix projected sequential pattern mining. So this is more efficient algorithm that skips the candidate generation altogether, unlike the generalized sequential pattern. So what it does is it uses a divide and conquer approach. It incrementally builds frequent sequences by growing them prefix by prefix. It starts with frequent prefixes and projects the database to grow longer sequences by appending the items that follow these prefixes. Each projection is smaller than the original, which makes this the search space much more manageable. For example, if a sequence pattern has A goes to B as a frequent pattern, then prefix span explores what comes after B by only looking at the parts of the data set after that sequence. So because of this, prefix span tends to be more faster and scalable, especially when the data set has many repeated patterns. So when to use the prefix span when the data set is moderately sized and dense, and when you want to avoid dealing with the explosion of many combinations of candidate patterns. And then we have the generalized sequential pattern mining, which is known as GSP. Now, this is a candidate generation pruning based algorithm that works in a BFS manner. This was one of the earliest approaches for sequence mining, and it works a lot like the classic a priori algorithm. It starts by identifying all the individual items that need the minimum support. Then it generates candidate sequences. Yeah, then it generates candidate sequences of length 2 from these items and filters them based on the support. And this process continues generating longer sequences, filtering out infrequent ones, and repeating until no more candidates can be formed. So now the issue with GSP is that as the sequence grows, the number of candidates can explode, leading to high computational costs. But for smaller, medium data sets, it's a very great baseline. So we have to use GSP when we want the explicit control over the pattern constraints because we are using candidate generation and pruning approach here. So we can use this for very sparse data sets. And then we have the spade algorithm, which is known as sequential pattern discovery using equivalence classes. So, and it takes a completely different approach. Here, it takes the vertical data format, which is known as ECLAT format, by representing the sequences using the ID lists. Uh, this is how it is generating the sequence IDs here. So, the destination bus stop is in the sequence 0, 4, 7, 8, 12, and respectively. And this is for all the destinations. So that is how we have formatted the data vertically. So in vertical format, each item or sequence is represented along with its IDs list, basically the list of transaction IDs and position where the sequence appears. With this, Spade can perform multiple intersections on these ID lists to find support counts without having to scan the entire database. It also uses equivalence classes to break the problem down into smaller independent sub problems, which can be also processed parallelly. So Spade is actually very fast when it comes to dense data sets and large number of sequences. So we can use Spade for large scale data sets. And this is the pseudocode and the followed by algorithm. So here we have seen for all the three algorithms, these are with the minimum support 3. With minimum support 3, these are the frequent patterns that have been generated. But if we are printing the top 10 patterns, these are the top 10 patterns that are getting printed. But if we actually see the frequent patterns with minimum support 3, the 10 is only restricted up to here. So after this thing, there are even more sequences with the same support. So we can't just randomly print top 10 or top 15 sequential patterns, because it has excluded other sequences with the same support as the 10th entry. So in contrast, we have used the top patterns with the support greater than or equal to 4 here, and it has taken the threshold support. So now it is not just top 10, but it is the top frequent patterns with this with the threshold that we have mentioned here. So it is not the emphasis was not merely on the repetition, but on how a sequence is unfolded in time and space. And then we have the Venn diagram. As you can see, this is the Venn diagram for the overlap of prefix GSP and spade. And the Venn diagram is a single circle, like it collapsed into a single circle, because as you can see here, all of the frequent patterns that we generated using the three algorithms are common here. But anything which is unique in these three patterns is none. So that means all these three algorithms produce the exact same set of frequencies for our data set and the support threshold. And so this Venn diagram visualizes the same. And it also tells us the toy data set that was created was clean, behaviorally consistent with the defined mining constraints. And coming to the results and key insights from sequential pattern mining, here we understood a very a main point here, which is the sequence grocery store to restaurant or restaurant to grocery store are not the same. It implies completely different. Here, it implies that a user did shopping and then went to a restaurant, but here a user ate and then went to shopping. So this is not equal when it comes to sequential pattern mining. So that is one thing. And second one, we have discovered some most common frequencies in which can be used further in some transportation analysis, traffic analysis, and all. And then we have the consistency across all the algorithm, as we have discussed. The Venn diagram was completely collapsed into a single circle. So this suggests that the pre-processing steps were good. The data set was crafted well, and the algorithms were also implemented successfully. And then we have some pattern-based inferences, such as routines that frequently begin at locations like gym or cafe, which is like gym in the morning. usually end with home or a restaurant. And we have some temporal behavior, such as some patterns appeared only during a specific time, such as gym in the morning, and if after gym, it was followed by playground for a recreational activity in early mornings, or then we have restaurant to office and office to restaurant during the lunch hours. And these are some limitations and ethical consideration that we have to consider. That is a part of the blog. So the conclusion we have here is, even a small data set can tell you big stories if you listen them the right way. This project taught me a lot about the pattern mining, interpretability, and the importance of the detail, especially when I use these three algorithms: prefix span, spade, and GSP. And this is the GitHub repository for both the dataset and the Google Colab notebook. And these are the references that I've used. Thank you.